Okay.
You are audible.
All right. Good. I didn't want to wear that anyways. What to look at and what am I going to see? Are there any radio astronomers in my area? Where can I get help? Can I do astronomy without the electrical knowledge or an engineering knowledge? And what do I do with my data? Okay, these are some of the most common questions I hear. One of the things when I got into radio astronomy, I was living up in Michigan outside the Detroit area, and I put a note out on the Michigan Astronomers website, and I says, are there any radio astronomers? I found one person. And I thought that I could rely on these people for help, knowledge, direction. It's not like a star party here. Last year we hosted a radio astronomy event 2 weeks after Peach State, and another microphone.
That one works.
All right. So we had maybe about 3 people show up. All right. And that's about all I was counting for. Because, like at Peach State, if you're having a problem with a telescope, like a brand new Dob, you can rely on a whole field of people. But with radio astronomy, it's I would say for every 250, 300 people, you might find one radio astronomer. So in the next couple of slides, I'll discuss some organizations that are kind of, sort of, involved with helping amateur astronomers. And so the first one is SARA, the Society of Amateur Radio Astronomers. It's just an organization dedicated to radio astronomy. Every summer we hold a conference at Green Bank Radio Astronomy site in Green Bank, West Virginia. If you ever want to visit there, it's open to the public. They have some historical radio telescopes. It is probably, out of all the observatories I've visited, professional observatories, Green Bank is my favorite. I mean, it is just a fantastic place to visit. The Astronomical League, the reason I put this up here is because they do have a radio astronomy listening program, or a radio astronomy program you can do. It has 3 levels: bronze, silver, and gold. I know Marie Lott. Her and I worked on it 2 years ago, and she was number 17 in the gold member, and I'm number 18. You can get a lot of information from them. What I'm going to focus on is 3 areas that I find the easiest for people to get involved with. The SID project is ran out of Stanford University, and it looks at the sky in wavelengths of 15 to 45 kilohertz. Now, your antennas in radio astronomy, the longer the wavelength is, the longer the antenna is. So to give you for instance, the antenna for the SID project, if you were to lay that out, would be 7 miles long. The next one is the Radio Jove. That listens to disturbances caused by Io and the sun, and you can even monitor the galactic plane with this. 18 to 40 megahertz is about the range. Your antenna is about 24 feet long. Your hydrogen line, or your 21 centimeter line, that you will be able to look at objects in the night or in the sky. That antenna is about 4 inches or so, 3 inches. And these would be about the easiest. Some of the other projects you can do is looking at meteors coming in through the atmosphere, what they call a forward scatter. That uses a frequency right around about 70 megahertz. So this talk is not going to be a talk that will give you a detailed aspect of one particular part of radio astronomy. It's just to give you a shotgun blast, get your feet a little wet, and it's going to be pretty quick. So with the Super SID project, as I said before, it's ran out of Stanford University, and what it looks at is the ionosphere during the daytime. Because with the ultraviolet light coming in from the sun, what happens, it strips away the electron molecule from the hydrogen atom. It causes our atmosphere to become more dense, and the radio waves reflect off of it. And as I mentioned in the last slide, we're looking at a frequency of 18 to 40 kilohertz. Well, who transmits off of that frequency? And it happens to be any country that wants to talk to submarines. This is all naval ran. Marie and I, we have listened to Russia, Germany, Italy, France, Great Britain, and of course the United States. What we listen for isn't the communications that they're sending. We're just listening to the carrier waves and seeing how it reflects off of the atmosphere. So this is the receiver. This is your typical mouse. The can is about the size of a soda can. And you can pick this up from the AAVSO organization. Sarah occasionally has this available on their website. I think this was about $75 when I purchased it. Very inexpensive. Just to give you a heads up, I think all 3 of these projects you could get into for probably about $1,200. Now, to put that in reference to things we have in our tool chest, I have a couple Ethos eyepieces that 2 of them ran me about that much money. And this is the antenna. This setup is at Marie Lottis Observatory.
My roll-off, yeah.
Yep. And I just made it 3 feet in. It's a 3-foot square wrapped around 18 or 16 gauge anneal copper wire, about 500 feet. There's 50 wraps on that apparatus. And when we were doing our project, I would turn it occasionally. I ran it east, west, north, south to see which frequencies we were getting the best. And it happened to be the one out of Cutler, Maine, and Puerto Rico.
So I feel like we kind of have it pointed to Puerto Rico. Really.
Pardon?
We kind of have it pointed to Puerto Rico, right?
Yeah. It's actually the opening's facing north and south, and the wires are facing east and west. So this is the typical data that you will see. It records this data about every 7 seconds. It will change. And what it's recording are these peaks. Go into much detail. But you can see this was a busy day. And one of the things with radio astronomy, especially with SID and the Radio Joe, one of the things we want to look for are these shark fin peaks. Those are the flares. And I like using a lot of analogies. So it's basically what happens is the sun sends this flare and we get it. And it's like if you went up to a stereo, turned it all the way up, and slightly turned it down. That's the sound that this produces. But you have to realize instead of some great music, it's just static we're hearing.
You can also see in that the difference between night and day.
Yes. So this is the day portion. These two lines here are the sunrise here at Deerlick. The black arrows are sunrise at the station that's broadcasting. And again, this is sundown here, and this is sunset at the station. And right here. So during the night, it becomes a lot, the atmosphere becomes transparent because those electrons then at night combine with the hydrogen atom. So the radio waves will just pass right through the atmosphere. So next is the hydrogen line. I'll get to Radio Joe next. You listen to radio astronomers and you'll hear jargon like the 21 centimeter line, 1440, 1.4 gigahertz every once in a while. Some people will refer it to the watering hole because it's at the 1420 mark is where, for all you ham people, the FCC reserves that area for scientific research. And no one is supposed to be broadcasting, at least in the United States, in that frequency range.
Is this where dishes come into
Yes.
play, like Ed and
Yep, we'll get there in one moment. It exploded in 1604. It was the last supernova seen in our Milky Way. Right now, this is right around a magnitude 20 object. I know with my 20-inch Star Master, there's no way I'm going to see that. And this data, when we do the hydrogen line, all we're doing is doing what radio astronomers call drifting. We park the telescope at a location, we let the object drift through our beam, and then we stop it once it passes. And these were all the scans that we ran for this object, and it takes about an hour to go through the beam. Here's a little bit more of a detailed object, a little cleaner, not so messy. These bumps here are actually interferences through the FFT algorithms. A typical scan runs about 1,800 different frequencies. And then it goes through that, and then it records it, and then it starts over again. And this graph is about 400 of those frequencies. So when I was up at Green Bank, I had access to the 20-meter scope, their 20-meter radio astronomy scope. And one of the things I was curious is to see, if I use a professional telescope, how much different will my data look to their data? You know, it's just like all you people, you'll look at a Hubble image or what other people have recorded to see how your data compares. And this is the little hump that I had that I thought was pretty interesting. And it was similar. Now, my graph was an hour long. This one was only 30 seconds. So it was a lot easier to get to this data. Now, one of the things about radio astronomy is the resolution of our telescopes really isn't very good. For instance, the resolution on my little 8-inch SCT, I think, is right around 7 arc seconds in resolution. The resolution on my 1.9 meter dish is 7.7 degrees. So that's why radio astronomers strive for these huge dishes to get these very narrow bandwidths. And when you see a radio image and it shows this nice hydrogen gas cloud, what they literally do is slice it like a slice of bread, and they just take the scope and go back and forth, and they'll just rock it like this. And it records each one of those passes, kind of the way I did with the drift scan. And then what they do is they just stack it and give it some false color, and that's what gives you the pretty radio image. None of my equipment will... there's no way I could ever do something like that. This is just another scan of a different object, Cassiopeia A. As in visual astronomy, we use the Messier objects, the Caldwell objects. In radio astronomy, we use the 3C catalog, which is kind of outdated. It's actually the Cambridge catalog, and it was done, like I said, in 1950, but those numbers are still used quite a bit.
And what exactly does that reveal to you information-wise?
So it shows you that there was a cloud up there, and as it's coming, it's showing me the intensity over a given period of time. Okay? Because when there's nothing there, it will look like this area right here. Okay? So, I don't know, I can't remember if we can see Cassiopeia A. And it shows me that there's a couple of bands there.
Is it kind of like a spectrograph, only at radio frequencies, so that when you see that spike at 14.447, 4.6 point, that reveals a certain level of hydrogen atom is getting ionized or?
Real close. So
What happens is the hydrogen atom, the electron, flips its spin. And when it flips its spin, it releases a tiny amount of electricity or frequency. And to do it, to record a single flip, it's almost impossible. But since hydrogen is the most popular or the most abundant gas, it happens a lot, so that's what we can record. And when you have an area like a supernova where the gases are expanding in that, that area is concentrated and those flips are then recorded. Does that kind of help?
I think so.
And different objects, like the 1604 object, didn't have these bands. And that flip that I was talking about happens at 1420, 508 megahertz. It's a very specific frequency. So these are the different alternatives you can look for hydrogen. This was developed by some math and engineering professors at the University of West Virginia. It's called the DESPRA telescope. You can make this for about $50. It's just a horn antenna similar to what Doc Ewing used. The scope in the box is just a Wi-Fi antenna that they retrofitted. I think they're selling this for about $300. And again, these are going to give you a very broad area of the sky. So Radio Jove is monitoring or looking at frequencies between 16 and 40 megahertz. It's probably my favorite part of radio astronomy. This is my setup down at my lot. Ed has referred to this as the badminton nets. We can, like I said, look at Io, and Io in its orbit around Jupiter gets squeezed. And at certain times, when it gets squeezed and it's in the right position, we can receive these frequencies here on Earth. And the two types of sounds that Io produces is what they call a long wave, and it sounds like waves crashing on the shore. And the short wave sounds like popcorn popping, and they're pretty distinct. So this is the setup of my antennas. These two run east and west. I need about 30 feet. And then I have a north and south. The north and south is mainly for the sun, and I can just run one antenna. The reason I have two is because Io's signal is so weak that it's almost like putting a second antenna on, and it builds with that. This is how I have 5 of these holes. With the Radio Jove, your antenna heights matter because it's working off of some of the reflection off of the ground. And that's kind of how they steer the antennas, because in the next couple of slides it'll be more relevant. But the lower Jupiter is on the horizon, the higher you have to put your antennas. So the three heights that we use with Radio Jobe is 10, 15, and 20 feet. And since most of the time I'm setting this up by myself, I devised this so it's easy. Those pipes go in the ground about 2.5 feet, and I just slide them in. And I put Roundup to keep them clear, because one summer I didn't, and I spent about an hour looking for my hose because the grass grew over it. This is the connection in the center. Again, this was for, this talk was for Sarah. And one of the things, when I first started, I would get here from Michigan, I would set up my antennas, and I would just throw them up. Didn't pay any sense to what I was doing other than putting them up in the air. And it took me about 3 years to get my first signal. And one of the reasons is, one, the sun wasn't in a good location, because I shouldn't say good location. The solar or the sunspots just weren't happening. And without the sunspots, I just don't get any noise from the sun. And the other thing was, I bet you I was flipping these around, and this side goes to the center post of my coax. So I was probably creating an interference pattern with it by having them go the opposite way. Because you want, if that string's on the right-hand side, I want the string on the second one on the right-hand side, because I want that signal to be built up. If it's on the one's on the left, it's just going to cancel each of the signals out. So I wasn't getting anything. For a long time, I thought my receiver was broke. I didn't know what I was doing, and both of them were probably correct. Again, the control room. This receiver is a single frequency receiver. It's centered at 20.1 megahertz, plus or minus a half a megahertz. The SDR play down there does the spectrograph, and then I have a calibrator to set everything to a known temperature, which you don't have to have, but instead of being just quantitative, it's a qualitative signal at that point. So here's the sunspots. Like I said, I started probably in late 2016. It wasn't in 2018 that I got my first signal. And again, when I started, Jupiter was as far south in its orbit as it could get. It's the worst time to start radio astronomy. One, I couldn't get a Jupiter signal. Sunspots weren't happening. I was almost lost, but I kept on coming back on vacation, setting it up, and just static. And I would call through all my data back home, looking for little blips. I wasn't even sure what I was looking for. And again, there was really no one I knew that I could take my dad and say, what's happening here? This is one of the radio signals that Marie and I got. We submitted actually this set for our bronze certificate. It is a short burst.
We were so excited.
Pardon?
We were so excited to see
Yeah.
that. Because it was like nothing, and then all of a sudden it was this.
Right. And the neat thing is, with Radio Joe, I can look to next year to see when the best possibility of listening to it happens. It's very, very predictable, and I'll go over that in one. That'll be the next slide. So this slide relates directly to the last slide. This is the portion of the IO. Each one of these signals, there's actually a fourth area that's very productive for IO signals. It's called IOD. And this is what I was talking about. I can plug in the day and time, and it will show me where Jupiter's going to be in relationship to these probability zones. IOB being the best. IOC probably is one of the worst places to look at it, and when we got it, it was pretty good. So this is the beam area of my antenna that it's watching. And I can tell because if this, I was steering this, I know this antenna was at 15 feet high. If this oval was centered over these two green lines, which are my antennas, that means I didn't have any steering. So mathematically, what they've done is caused the antenna to look a little further south than just straight up. This was my first my first son data that I got. I was pretty excited when I got it. And with Radio Joe, you can upload your data to a NASA website. And so actually you could kind of say you work for NASA. If you want to push the envelope. Radio Joe is probably the best out of the three areas to share data. There are probably about 40 to 50 observers that constantly put up their data. And a couple of them are really good. And when I have a question, do I have a legit signal that I captured? Those are the people I go to for their data. In the next two slides, this is one of the gentlemen. This observatory is outside of Pittsburgh. He caught the same signal as I did. His name's Chuck Brown, I believe. And then the Muskegon Community College in Muskegon, Michigan recorded this. This was probably a student project or a physics instructor's project that he was using to show the students. This data, what I was doing is this is a 24-hour scan of the sky with Radio Joe. And what you can do is you can measure the galactic hump over a period of, let's say, 6 weeks
if you do this once a week, this hump will move one way or the other depending on the season. And when I saw this data, I was almost broken because I noticed these very uniform interference lines. And for the people here at the village, I blamed everybody for interfering in my data. I swore I was going to turn on my headlights every night. So, but I owe them a big apology. What this turned out to be is a little speaker that had a rechargeable battery. And as the speaker would die, it would kick in to recharge itself, and that's what those lines were. It took me a year to figure that out, that I caused the RFI. It was your speaker. It was my speaker. I'm guilty, you know. These tall lines over here, those are called sweepers. Those are produced out of Texas by the military to do exactly what we're doing with SID. And that's just to monitor how reflective our ionosphere is. Those happen about every 3 to 4 minutes or so. Now this data is RFI. RFI stands for radio interference frequencies. And what happens is it's kind of like the white light of radio astronomy. This happened right about 2 weeks after the hurricane last year. We were having a very nice quiet day, and then all of a sudden, shortly after noon, it went nuts. Now, Tom Crowley outside Atlanta was recording it. John Cox up in South Carolina was recording it. I was recording it down here. But people in Florida and Missouri, they didn't see it. So it was something that was happening here. And it was really unusual because this was the first time I saw it. And this is just a waterfall of the area. Typically, this area is pretty clean because, like I said earlier, the FCC bans commercial traffic or even ham radio operators from operating in that frequency. So whatever it was pretty significant. I've heard people have commented on it was a Christian radio station, it was a TV station, it was because of the hurricane. I haven't been on lately, so I don't know if that's still happening. When I talked to John a couple of weeks ago, he says it's not as bad.
What frequency?
20 megahertz.
Eric probably has something going on in his basement.
No. I'm thinking military.
So, for anyone getting involved in radio astronomy, just a few tools are needed. Some of them you probably already have. You can purchase all those tools from Harbor Freight, is where I got all those photos. You can get away with that for about $100 in extra or specialized tools. The ones that I would recommend is a good soldering iron. The stations work very well. And the flush mount cutter, extremely useful. and then your VOM. Those would be the three. The screw, and the wire strippers, gotta have those. Everything else is optional. So here's some of the favorite sites that I go to. Sarah, the Astronomical League, I have Astronomy League, me bad. The Space Weather Prediction is run by NOAA. That's for the Radio Jove. I can go in and they have every flare that happens. They have stations around the world, so if it's nighttime here in Italy, it's morning. So they record exactly what happens. Radio Jove, the SID project, the Groups I.O., the Radio Jove is probably the best. The SID, the Super SID, it's more, I have a problem what's happening with the system. Back, I think in December or something, our data wasn't being uploaded. What happened is they had a flood at Stanford University, a pipe broke, and their system was down for about 2 months. And Radio Sky Publishing, Jim Sky owns that. He is very helpful. He does a lot of the Radio Joe software. And then the other one that's very good that I use a lot is Radio Eyes for the 21 centimeter line. A very useful piece of software. It is free, but he limits you to a half-hour a day usage. And I think he only charges like $12 for a license or something like that. And with that, thank you for listening. Are there any questions?
What was the frequency that the FCC bans traffic on?
One of them's right around the 20 megahertz. At 20.0, you have the WWV out in Boulder, Colorado. Is it? Huh? It's a timestamp. There's a couple of them.
It's 5, 10, 15, and 20 acres.
And that system will pick up that from Boulder on my little receiver. I can hear it.
I just want to comment that if someone gets excited about this but wants to get their feet wet, they have adult summer camp at Green Bank. You can go for 3 days to StarQuest, and you can stay there and you can use their telescopes and get some data. And that's a radio-free zone. I mean, you have to leave your cell phones at home and.
Oh, you can take your cell phone.
Yeah, but I mean, you can't.
There's no towers for 60 miles.
So it's a radio dark site. So, but anyway, it's called Green Bank, West Virginia. Just Google Green Bank Observatory, and I think it's called StarQuest.
StarQuest, or even go to Sarah. Yeah. Sarah's runs for 4 days. Some of the back behind the stage things that we do are pretty awesome. Like there's a 300 meter telescope there. I've been on top of the control room up on the scope, and I don't like heights, but I told myself, just suck it up, Buttercup, you're going on top. Because it's kind of cool. I got a picture of me standing right next to one of the receiver horns.
Nice.
Yes, ma'am.
Okay. And a question for Marie as well, and Nico. What do you find most fulfilling about it? Like, what's the big wow, I just heard something, realized something, captured something? If
you talk to some of these guys here, they will tell you that I'm
visual observer, much like Marie is. I'm not into imaging, and I want it to be different. And radio astronomy, when I first heard about it at StarQuest, a gentleman that I met was talking about Radio Jove, and I didn't even understand what Radio Jove is. And over the 3 days of talking to him, he piqued my interest that, okay, this little receiver, I can throw up some wires and I can listen to Jupiter. That's different. That's kind of cool. And the longer you do it, radio or Jupiter Io on that probability chart, even though she comes to the dance, she may not dance. Okay, so Marie will tell you, we had it. We ran our data or our signal, looking for the signal for 2 hours. It was supposed to happen. It had a 90% probability that was going to happen. Well, 10% was still saying, no, I'm not dancing. So, but once you get the signal, and it's like, wow, this all works. And like Marie was hosting some Girl Scouts here, and I first hooked up my 21 centimeter dish, and they came down to look at the itty bitty telescope that we did for our project, but I was more interested in the 21 centimeter line because I hooked it all up and it worked the first time. You know?
Normally not the case. I like it because you do it during the day. It's all daytime, and it's kind of tricky because you're pointing this big dish at something you can't see because Jupiter. I mean, it's up. You know, you can't see it in the daytime. You know, and then you're trying to kind of think of it as a net basket in a sport, and you've got something you can't see that you're trying to point in the middle of at the right time, so that when it walks past you, you can catch it in the basket, you know. And so it's kind of fun like that because it's like fishing or something. You're sticking everything out and hoping the fish swims into your net and stays there. But you know, you don't know if you really get it or not. But it's during the daytime work.
We can discuss it later because I think my time's up. We got one more question.
Oh, okay. You mentioned remake of the radio quiet zone.
Yes.
In order to properly. Georgia has a really interesting radio zone defined what is naturally produced. Down by Warm Springs, Woodbury, in that area, there is a very, very old impact feature which gives you a crater shape. You can see this on topographic maps. That by is naturally really quiet, it does not have signals from anywhere else. And one of the local universities has some fairly large radio dishes down there already. But I would imagine if you're looking for somewhere that you need to find a nice portable site for your investigation, you could just drag them down there. Take a look.
Well, to tell you here, when I showed my data to people up in Green Bank and that, they were shocked on how quiet Deer Lick was. Because besides no lights, that means there's no machinery in that, so it's pretty quiet.
One more question.
One more. Are you familiar with Perry? Pisgah?
Yes.
I was up there some years ago. It's in
Up in North Carolina?
Yeah, Pisgah Research Institute. Their satellite dish has a smiley face on it.
Yeah.
Because when the Russians would go over, they wanted to let the Russians know we see
they were
you too.
smiling at us, yeah.
But that's a neat radio observatory with dormitories.
Thank you, Dave. So